This seminar will talk about derating and lifespan of power supplies. First, we will discuss two items that are necessary for the thermal design of power supplies: the type and concept of derating and the lifespan of the power supply. First, in selecting a power supply, it is important to consider the heat generated by the power supply itself. For example, for a power supply with an output power of 100 watt and an efficiency of 92%, the internal power loss dissipated within the power supply is 8.7 watt. The higher the power consumption, the higher the temperature of the components inside the power supply, and the higher the ambient temperature of the power supply. Note that increasing the load factor in a high ambient temperature environment increases the component temperature, and deviating from the rated temperature of the component increases the risk of failure and on the lifespan of the component. There are two main derating curves for power supplies. The first is output derating, and the second is input derating. These two derating characteristics are described in the catalog for the applicable power supply. Now, I will explain output derating. Output derating characteristics differ depending on the installation orientation of the bare board power supply. For example, in a installation that is flat, when components inside the power supply generate heat, there is little effect on other components. However, in D installation that is attached to a wall, if components inside the power supply generate heat, the warm air rises and heats up other components, affecting them. Since D installation on a wall has a smaller margin relative to the rated temperature of the component compared to A installation that is flat, resulting in a lower usable load factor at the same ambient temperature, changing the installation orientation from A installation to D installation changes the output derating characteristics. This is a graph of output derating. The horizontal axis is the ambient temperature, and the vertical axis is the load factor. The higher the load factor, the higher the electricity loss inside the power supply and the higher the component temperature. So the power supply should be used in an area with a lower ambient temperature. The higher the ambient temperature, the smaller the usable load factor of the power supply. The bare board power supply can be used up to 100% of rated output current with A installation and 50 degrees Celsius ambient temperature. Next, let's look at the output derating curve for D installation. Due to the location of the components in the power supply must be used at approximately 80% or less of its rated output current at an ambient temperature of 50 degrees Celsius. The output current that can be used at the same ambient temperature varies depending on the installation direction, so please check in advance. Additionally, the derating characteristics differs by product, so also check the output derating column in the catalog. It should be added here that the ambient temperature of the output derating is defined. First is the case of a naturally air-cooled power supply. The ambient temperature measurement point is 50 to 100 mm lateral to the power supply, which is not affected by radiation due to heat generated by the power supply or convection current of heated air if the power supply is close to the ambient temperature measurement point. Next is the case of a forced air-cooled power supply. Since the air temperature at the inlet is the ambient temperature measurement point, the ambient temperature measurement point for products with a built-in fan also differs in accordance with the fan's wind direction. For an intake fan, the ambient temperature measurement point is 20 mm away from the fan, and for an exhaust fan, the ambient temperature measurement point is 20 mm away from the I/O terminal block. To avoid obstructing the flow of cooling air from the fan, please pay attention to the placement of peripheral parts in the fan installation area and ventilation slots. The next section discusses input derating. Input derating is represented by a graph with input voltage on the horizontal axis and load factor on the vertical axis. The required input current increases when the input voltage is low. Therefore, the available load factor is smaller due to increased component electricity losses and heat generation at the power input. In this case, when the input voltage is 85 VAC, it is necessary to use the device at no more than 80% of the rated output current. Note that input derating may not be set for each product, so please check the derating items listed in the catalog for each product. The available load factor can be calculated by multiplying the rated output current by the output derating and input derating. For example, if a power supply with a rated current of 10 amperes is used with natural air cooling in the A installation configuration, the output derating is 80% at an ambient temperature of 55 degrees Celsius. When using an input voltage of 85 VAC, the available output current is 6.4 amperes because the input derating is 80%. Next, let's talk about the lifespan of the power supply. When selecting a power supply, please check the lifespan of the power supply as an indicator of the timing to maintain the power supply. The lifespan of the power supply depends on your operating conditions. If you want your equipment to run longer, please check the estimated lifespan of the power supply for each operating condition. The two consumable components of the power supply are the built-in aluminum electrolytic capacitors and the fan. For bare board power supplies without fans, aluminum electrolytic capacitors are consumable components. For unit-type power supplies equipped with a fan, either the fan or the aluminum electrolytic capacitor, whichever has the shorter lifespan, is the consumable component. If the fluctuation range of self-heating inside the power supply is high due to changes in ambient temperature or load factor, there will be a difference in the thermal expansion coefficient of the component materials, causing repeated distortion in the solder joints. This distortion causes connection failures, such as deteriorated joint strength and cracks in the joints, leading to the end of the power supply's life. Let's talk about the lifespan of electrolytic capacitors. Electrolytic capacitors reach their end of life due to the amount of excess electrolyte and the evaporation of the electrolyte through the rubber seal, and the speed of evaporation is determined by the temperature of the electrolytic capacitor. The relationship between lifespan and ambient temperature is governed by Arrhenius 10 degrees Celsius doubling rule, which states that a 10 degrees Celsius rise in temperature halves lifespan. The following is an example of the estimated lifespan of a bare board power supply in the A installation configuration. The estimated lifespan at an ambient temperature of 50 degrees Celsius and load factor of 70% is 48,000 hours. However, cooling the power supply and lowering the ambient temperature by 10 degrees Celsius can extend the estimated lifespan to 96,000 hours, making it important to reduce the ambient temperature. Estimated lifespan graphs for electrolytic capacitors are available on the technical data or download page on the model page of our website. Now let's talk about fan lifespan. Fans reach the end of their life when the internal bearing lubricant film wears out due to friction. This lifespan shortens as the ambient temperature rises, but the lifespan acceleration factor depends on the fan variety and speed, ambient temperature, and other factors. Please be careful to ventilate the power supply and equipment to prevent heat generated within the equipment from accumulating. For example, in the case of a unit-type power supply product with a short fan lifespan, the estimated lifespan graph published on our page is the data for the estimated fan lifespan. From the estimated lifespan graph, the estimated lifespan value is about 80,000 hours at an ambient temperature of 60 degrees Celsius and a load factor of 50%. However, the estimated lifespan can be extended to about 100,000 hours by using the power supply at 50 degrees Celsius, 10 degrees Celsius lower than the ambient temperature, so it is important to reduce the ambient temperature. Please also consider the lifespan of the solder. Under conditions where the input voltage of the power supply is turned on and off every few hours during the day, or where the device repeatedly cycles between standby and operation every few hours, the solder joints of components are subject to repeated temperature changes and are prone to cracking due to thermal fatigue of the solder. Estimation of solder lifespan due to thermal fatigue can be calculated using the Kaufman-Manson relation based on the temperature difference of the power supply and our temperature cycling test results. For example, according to the estimated lifespan graph of the MG series, due to thermal fatigue, if the number of on-off cycles per day is 1 and the point temperature difference is 75 degrees Celsius, the estimated lifespan is at least 14 years. But if the number of on-off cycles per day increases to 2, the estimated lifespan decreases to approximately 8.5 years. To extend solder lifespan, the number of on-off cycles should be reduced, or the temperature difference between temperature measurement points should be decreased. This concludes the seminar on derating and lifespan of power supplies. Thank you for watching.